Alright, so this is going to be Note 5 from CS70. This is going to be on graph theory, and this one is going to be pretty intensive, but it's going to cover a lot of important information. So let's just get started. So what is the purpose of graphs? Basically, it's to take something that's complex, that usually involves networks of some kind, and boil it down into entities and the connections between them. So it's to help us model real-world phenomena. And we're going to look at an example called the Königsberg example. And, this is kind of the map. We have two lands over here, and then we have an island, two islands, and then we have these bridges between them, and the goal is to walk across all 7 bridges and end up at your original starting point. And I think you can only cross each bridge once. And to get a more simplified version of this, we're going to convert it to its graph equivalent, and that looks like this. And we can just quickly verify that this image, this map, is the same as this graph. We're not going to go through every example, but just looking at, for example, island B, we see that it has 2 connections to land A and 2 connections to land D. Similarly, island B has 2 connections to A, 2 to D, and then island B also has a connection to island C, so B is connected to C. And you can test that out for every land. Each land is represented by a vertex, and each bridge is represented by an edge, where an edge is the line between 2 vertices. Okay, that's pretty much why they're the same. And what must be true for each circle to only be visited once? So in order for us to go once and not reuse edges, we're going to have as many bridges, we're going to have as many paths going from one vertex to another, or one land to another, as there are paths going from that land back out to the other one. So as many in as out, essentially. So, to say that a little more succinctly, each circle in the graph must have as many paths going into it as going out of it. I think the idea is pretty straightforward. I can really quickly just illustrate this in Paint, and let's switch over. So let's say we have 3 lands, A, B, and C. As we can see, each land has as many paths going in as going out. So for example, if we were to start on A, we can go into B and then out B, and then that also goes into C and out C. And so we'll be able to end up where we started. Okay, and we'll sort of formalize that a little bit more later. But I believe for now we're going to move on from the Königsberg example and take a look at some formal definitions of graphs. So, an undirected graph is a graph where the connections between nodes do not imply a direction or like an order. So, we're going to label the set of vertices in a graph as V. Capital V represents a set of vertices, and then capital E represents the set of edges. And this is the vertice representation. Each vertex corresponds to each land, and then these are the edges. They're undirected. I don't know why this is here. That does not need to be there. But A connects to B. This is why, because there's 2 bridges. Yeah, that's why, because it's a multi-set. There are 2 connections between 2 nodes, and usually in this class, I don't think we're going to be dealing with multi-sets. I think they said that somewhere in the notes. But yeah, multi-set is any case where there are 2 edges running between 2 nodes. And in an undirected graph, this is not necessary. Once we establish a connection between 2 nodes, like we can travel in either direction. And then a directed graph is where it's kind of like a one-way street. You have to start at a specific node, and you can only go to another node as long as it's pointing there. I can briefly explain what this means. This is the cross product of the set of vertices, and this represents every possible edge going from one vertex to another vertex in a set of vertices V. So that's that. Edge notation, right, it changes slightly whether we're dealing with a undirected graph or a directed graph. So for an undirected graph, the order doesn't really matter. Basically, we have a set that's denoted by E, and then we have pairs, which are technically also sets, that are in that overarching E set. And those pairs represent the connections between some node in V to some other node in V. And if we are dealing with an undirected graph, it doesn't really matter what order the vertices come in, but if it is a directed graph, then the first vertex points to the second vertex. And so you must sit at the first vertex and go to the next vertex. So order matters in directed graphs. Let's see what this example is. So this is an undirected graph. It's asking us what are the vertex sets and what are the edge sets. So, the vertex set is just a set of the numbers 1 through 5, and then the edge sets, we have a pairing of 1 and 2, 1 and 5, 5 and 4, 4 and 3, 3 and 2. Yeah. Okay, and this is a more concept check. So we're going to say that an edge between Alex and Bridget means that Alex recognizes Bridget. So given this, we don't necessarily know if Bridget recognizes Alex, so we would treat this as a directed graph. Alex points to Bridget. Bridget doesn't necessarily point to Alex. However, if they know each other, then we could just use an undirected graph. They have that connection between them. And now we're going to dive into a little bit more terminology. First word we're going to look at is incident, and that just means that refers to an edge that is connected to some vertices U and V. So the way that it's used in context is an edge is incident on vertex U and vertex V. Neighbors refer to two vertices that are connected by an edge. The degree of a vertex refers to the number of edges coming out of that vertex. And for an undirected graph, there is just one definition of degree. But for a directed graph, there is something called an in degree, which is the number of edges going in to a vertex, and an out degree, which is the number of edges going out from a vertex. Okay, so that's that. Isolated vertex is essentially just a vertex that has no connection to any other vertex. A self-loop is a self-evident, yeah. It's a vertex that connects to itself. A path is a route from one node to another, and it's not necessarily the shortest. Let's just imagine, and I believe this is the example they use in the notes. Let's just switch over to Paint. And let's imagine, I guess we don't have to imagine, we can draw it out. I think in the notes they call these houses. So a path is essentially any traversal of this graph such that we don't go over vertices again, we don't go over edges again, and we don't necessarily start where we end. So, and also a path doesn't have to be the most optimal one. For example, this from here to here, that's a path, but this is also a path right here. I probably should use a different color, but I think you get the idea. The next definition is, let me switch back, is a cycle. So for us, a cycle is a path where the start is equal to the end. And let's see what exactly. It basically leads you back to where you started. A walk is just a traversal of the graph, and you can repeat edges, you can repeat vertices, and start might be equal to end, but it doesn't really have to be, I think. And then a tour is a walk where the start and the end have to be the same. So let's look at this chart to get a better sense of it. So, to keep these words straight in my head, 1 second. Right, so a walk, no repeated vertices, no repeated edges, start doesn't really equal end. A path, yeah. Or, sorry, I guess I said that wrong. So we can repeat vertices for a walk, we can repeat edges for a walk, and start is not necessarily equal to the end. A path, we don't retrace any of our steps, and the start is not necessarily equal to the end. In just a regular old tour, the start must equal the end, but we can, the start must equal to the end, must be equal to the end, and we can't repeat. And, no, we can, sorry. Don't listen to me, honestly, just look at this chart and understand what it's saying, because saying it out loud, I get confused between an empty spot and a check, but anyways, just think about that, okay? Not what I'm saying. Okay, disconnected graph representation isn't super important. They're asking us what V, the set of vertices, would look like. So basically, it would look like one set, and then it would have 3 subsets for each of these graphs, subgraphs, essentially. So, 1, 2, 3, 4, 5, 6, 7. It's fairly self-evident, I think. So now we're going to move back over to the Königsberg example to talk about something called an Eulerian tour. So we're going to claim that an undirected graph G has an Eulerian tour if and only if G is even degree and connected, except possibly for isolated vertices. So just to define a couple of things, when we say if and only if, we're going to have to prove both directions, meaning we're going to have to say, if there's an Eulerian tour in G, then the graph has nodes that are all of even degree and connected. And then we're also going to say if there is a graph that has nodes that are all of even degree and they're connected, then you can perform an Eulerian tour on the graph. So I'm going to prove the forward direction, and this is my notes. They're kind of dense. I wouldn't recommend reading through this. I'm just going to kind of explain what this is. So the tour we can't repeat. I think this is a mistake. We can't repeat vertices. We can't repeat edges. However, the start must equal the end. And as we sort of talked about earlier, if the graph is even, then, and when the graph is even, it means that all nodes have an even degree. If that's the case, then we can start where we ended up, but let me formalize that a bit more. This is essentially saying that, if a graph has an edge coming out of it, then that must connect to another vertex, and that means that every vertex with some edge coming out of it is connected to every other vertex in the set of the connected graph. So honestly, this part's not important. The important part is kind of like that representation we did earlier, which said that if each node you go in as many times as you go out, then it's the case that you can end up where you started. And what we do here is, say we start here, and I just draw the example again. It'll be that simple 3-vertex graph. Save. Okay, let me make sure I switched over. Yeah, okay. Okay, really quick, I'm like not even really gonna label everything. Let's just say we start at the bottom node and we want to perform a tour such that we travel over edges and vertices once and we end up where we started. So we can perform a tour on this because every vertex has an edge that allows us to enter the vertex and then leave the vertex. And you know, we can pair them up. So this is the enter and this is the exit for this node. This is the enter and exit for this node. And then the only time they don't happen one after the other is for the very start. But yeah, this is, I feel like I repeated myself a little bit, but hopefully the idea is clear now. So we're going to switch back over to the notes and get into some of the more interesting stuff when it comes to this algorithm. So that was the direction where we assumed that we can perform an Eulerian tour. We were just kind of showing that it must have even degree, but we're going to say now that if it's connected and has even degree, then we can perform an Eulerian tour. So we're going to, the notes mention something called like a find tour method, but I had to watch the lecture for this, and I believe that they did a much better job in lecture explaining this than they did in the notes. So these are essentially the steps that we have to perform, and I will mention the step name and then describe it with each visual. So all we do is start off by taking a walk, and we actually want this walk to end up where we started, and we'll see why. So, you know, say 1 is the start, and we're just going to take some arbitrary walk through the graph, and we're going to end up where we started, which creates a cycle. And that cycle is going to be labeled as C. And what we're going to do now is remove all of the edges in C from G, our graph G. So notice how all of these edges are now gone. So something to note is that because this Eulerian walk was actually a tour, an Eulerian tour of that graph C, that means that we must have traveled over an even number of edges. And hopefully that makes sense, because every node in the graph C must have been even degree. So we must have traveled over an even number of edges. And because of that, each subgraph still has an even degree, meaning every node in each subgraph still has an even degree, because you subtract an even number from an even number, you get an even number. Is there anything else that I'm missing? Yeah, so we're going to label these subgraphs as G1 through GK. And I mean, this is sort of trivial, but it was necessary to mention that, you know, we know these can be connected back together because each of these subgraphs were incident upon edges found in C, right? Which basically just means that this used to be one connected thing, but then we found some subgraph C and we just took out all of those edges, but we can like obviously put them back. That's pretty much what that's saying. And then we recurse, or induct I guess, on each subgraph, and we find that if it's the case that each subgraph can perform an Eulerian tour, then, you know, we will bring it back together by splicing together these subgraphs at the points at which we slice them off from C, if that makes sense. So notice how this black traversal right here is the same as this black traversal right here, and we're connecting this red subgraph first at this point right here. Okay, so that's how we algorithmically determine if there is an Eulerian tour in a specific graph. Okay. I can just leave these up for you to read if you want. Let me make sure that's not in the way. Yeah, okay. So we're going to move on to some even more interesting topics, which are about graph properties. So the first thing we're going to talk about is trees, like very briefly. Yep, connected and acyclic graph. Going to talk about them more in this section right here on trees. So next, this is sort of terminology in the beginning. A side is an edge that bounds a face, and a face is essentially a segment on a graph. And I will illustrate all of this in a little bit, but I'm just going to get the words out on the page. And then a bridge is kind of just an edge that connects two components of a graph. And then planar graphs are pretty great. There's a lot of cool properties that go along with them. So I'm sort of just name dropping, but I'm going to bring them together when we start describing things. So a planar graph is a graph that can be drawn in such a way that edges in that graph do not intersect. And there's this other notion of a bipartite graph, which is represented here, which is a graph in which you can take half of the vertices, or at least divide the vertices into two groups, and have edges going between vertices in different groups, such that edges do not go between vertices within the same group, if that makes sense. So we're going to have this left group of vertices and this right group of vertices. And I think it should actually be that. Yeah, that's right. And hopefully this makes sense. This is the union of all of the nodes found in that left set and that right set. And then this is the cross product between elements in the left set and the right set. Okay, and a simple graph, which I don't think it's explicitly mentioned, but it's important to note for some of the things we're going to talk about, is a graph that does not have a node with a loop on it, and there is also no double edges between nodes. If you remember from before, we had graphs called multisets in which a node had a bridge going one way and a bridge going that other way, but simple graphs do not have that. And we're going to move on to the handshake lemma, but I need to take a break for a second. Okay, so before we get into the handshake lemma, I think really quick I'm just going to very briefly talk about these. These top graphs are planar and these bottom graphs are non-planar. Notice how these do not have edges that cross over each other. This graph is actually the same as this one, but these do have edges that cross over each other. And these are two special graphs. This is called K3, 3, and this is called K5. And I think we're going to get to, we're going to get to that in a little bit. But so now for the handshake lemma. So the sum of the degree of vertices, the sum of the degrees of the vertices in a simple and planar graph is equal to 2 times the number of edges. So let me make this clear. We're going to switch over to Paint, and I'm going to draw a non-planar or a planar graph. So don't save. Okay. So let's just say, maybe we have a graph that looks like something like this. Oh, that's familiar. And I'll have something that goes like that, right? Yeah. Okay. So one of the properties was that I already forgot. What was it? The sum of the degree of the vertices is equal to 2 times the edges. Right. Okay. So we have, let's just count the number of edges. We have, 1, 2, 3, 4, 5, 6 edges. And 2 times e is equal to 12. So I'll just write that 2e is equal to 12. And we're saying the sum of the degrees of each vertex is equal to this number right here. So let's just count the degrees of each vertex. So this has 1, 2, 3 edges coming out of it, and this is 4, 5, 6, 7, 8, 9, 10, 11, 12. So as we can see, the sum of the degrees of the vertices is equal to 2e. Okay. Another interesting thing is relates to the faces. So I think the let's see exactly what the note says. Let's switch back over really quick. Yeah, so the sum of the degree of the faces is also equal to 2e. Okay. So that sort of gets into something interesting called duality, which I believe we'll talk about in a bit. So we're going to count the number of faces, and to define faces, it is a section of our graph that is completely surrounded by edges. So for example, that would be a face, this would be a face. I mean, I think you get the idea. Another interesting thing for graphs is that we have to count for planar graphs. There's technically a face on the outside or bottom side, and let me make this more clear by drawing a cube. So I'm going to try to draw the 3D representation of a cube to the best of my ability. So this is a cube, and a cube can actually be drawn in a way such that no edges touch each other. So a cube is actually a non-planar graph, and the typical way of drawing this is like this, and you can sort of imagine this as us like crushing the cube such that the bottom kind of gives out from underneath itself and flattens out. And what we're going to notice is that if we think of this as a cube, there is 1, 2, 3, 4, 5, 6 faces, where the 6th face is on the bottom side. So at least for me, that's kind of what helps me reconcile with the fact that these graphs have a face on the other side. Okay, I think this sun's in my eyes. Let me pause for a bit. Alright, so we're going to move on to that next part, which says, okay, we basically want to say that for every connected planar graph, the number of vertices plus the number of faces is equal to the number of edges plus 2. And, depending on what problem you're given, you can obviously manipulate this equation however you want. This is true, and I'm not really going to formally prove it. What I'm going to do is just draw an example. I guess maybe I can formally prove it. I'm just going to talk through it because you get a more intuitive understanding from actually seeing pictures. But so, if we have 0 edges, then that means, say we have one vertex, that one vertex is going to have 0 edges, and a graph with one vertex by default has that one face. So, 0 edges plus 2 is 2, and then one vertex plus one face is equal to 2. So base case holds. Now we're going to assume that this holds for a connected planar graph with edges greater than or equal to 0. And the first case is we create a tree, and again, a tree is an acyclic connected graph. There's no cycles in the tree. And let's see. we know that this is sort of a fact. I think we prove it at some point, maybe later in the notes, but we know that the number of edges in a tree is one less than the number of vertices in the tree. And a tree is actually the minimum number of edges necessary to connect all nodes in, honestly just all nodes in a graph. Think of a linked list. Say there's 3 nodes, and you just have like node 1 connected to node 2, connected to node 3, and notice how there are 3 minus 1 connections between all of them. A linked list is also a tree. And then what if it's the case that we have a cyclic graph? Well, because we proved that trees hold under this condition, and you can sort of take a look at the math here. Basically what we do is we remove edges from our cyclic graph until we get a tree, and then we know that the tree holds, and so we take note to like look at when we're adding those extra edges that we removed, the formula still holds up. But enough talking about the proof, let's get an intuitive understanding of why this works. So to do that, I'm going to draw out just 2 examples. Let's see. This one is going to be a planar graph that looks like this. And this is one in the picture that I showed. Actually, both of these can be found in the picture that we saw earlier. I mean, I just drew the one that I'm drawing right now, but yeah. Okay, and then we're going to say, we're just going to keep track of the edges, the faces, and the vertices. Okay, so I'm just going to mechanically go through this. And we're going to see that there are, 1, 2, 3, 4, 5, 6, 7, 8 edges. And there are, let's switch to another color. 1, 2, 3, 4, 5 faces. I think I might have done something incorrect, but give me 1 second. And then there are, let's see. Hi. Let's see. There's 5 vertices, right? So if we remember what the formula was, it was vertices plus faces is equal to 2 plus the number of edges. And, if we add 2 to this, we get 10, so the equation holds up. Let me just write the equation so we have it on hand. Vertices plus faces is equal to edges plus 2. Okay, just really quickly, we're going to look at this one here too. So, number of edges: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, number of faces, that's going to be 1, 2, 3, 4, 5, and 6. And number of vertices is going to be 8. There's 4 here, switching to a different color. There's these 4 here, and then there's these 4 on the bottom. 8 plus 6 is 14, so we have 14 over here, and then we add 2 to the number of edges. That also gives us 14. So yeah, that's why that holds. And let's look at the next part. Okay, so we're actually going to use some things that we talked about earlier to prove this next piece, which states that the number of edges is less than or equal to 3 times the number of vertices minus 6. And yeah, let me draw some things really quick. Okay, so as we saw under the handshake lemma, these two properties are true. The sum of the degrees of all the vertices in our graph is equal to 2 times the number of edges, and similarly the sum of the degrees of faces in our graph is equal to 2 times the number of edges. Now, the graphs that we are dealing with are planar and simple, and because they're simple, they don't have loops, like a node does not loop onto itself, and there are no dual edges between nodes. So there wouldn't be no secondary edge like that. And so like the minimum smallest simple planar graph, I believe, is this. And counting the number of faces, we have just 1, 2, and we see that there are 3 edges. So something we can establish is that I believe if there are 2 faces to a graph, I think it's this. I mean, what do we have in notes? Just gonna check really quick. Oh, no. Yeah, that was incorrect. Oh, give me 1 second. 2 edges. Sorry, so what actually should have been done is we wanted to find the degree of the faces. So we have one face here, and then we have another face here. Again, considering that this is the simplest simple and planar graph, we're going to notice that this face right here is of degree 3 because it has those 3 edges creating it, and similarly that interface also has these 3 edges that create it. So the degree of faces is equal to 6, and the number of edges, and I don't know why I just deleted the whole graph, is equal to 3. So we can say that the number of edges must be less than or equal to 3 times the number of faces. And from there, we are actually going to pull in, and give me 1 second. Okay, so, sorry, this should have been a little bit more concrete, so let me explain. So we're going to have this graph here. This is the minimum number of edges required in order to create a face. We sort of showed, this does not, this does not count as a face in a simple graph because you can't have 2 edges going between vertices. So you need at least 3 edges to make a face, right? And you could also have 4 edges to make a face. What we're going to notice here is that you're going to need, let's see, you can have greater than 3, but basically because we have these 2 faces here and the degree of the face of each face is 3, that's going to in fact be equal to 2 times the number of edges in this case. But in this case, 2 times the number of edges is 8, which is greater than or equal to 3 times the degree of the faces, which is, there's 2 faces, and they're each of, so it's not the degree of the faces, it's just the number of faces, so it's 6, yeah. Okay, sorry, that was a bit confusing, I think, but hopefully it makes sense now. From there, we're going to bring in they're all called Euler's theorem, but I think this one was like 5.1 or something, and we're going to say that V plus F is equal to E plus 2, and we are going to, if we remember, the original inequality we were trying to show was that our E was greater than or equal to 3 times the number of vertices minus 6, and so we're going to sort of get it into that form by noticing that we're just going to multiply this by 3v. That's going to be equal to 3e minus 3v plus 6. And then we see that 3f is less than or equal to 2e. So we're going to say the following. Give me 1 second. So given the inequality that 2e is greater than or equal to 3f, what we're going to do is basically treat this as 3f and then put it alongside that. So we're going to say 3e minus 3v plus 6 is equal to, it's not equal to, it is less than or equal to 2e. And we're going to just do some manipulation to find out that e is less than, e is actually, let me see, did I say this right? Less than or equal to, 1 second. I think I might have flipped the sign somewhere. I think in here it might be less than or equal to, let me see. Yeah, so, sorry. This is, I wrote this equation from memory. This is what the equation should actually look like. So, yeah, basically, again, from here, we're just going to isolate e, and we're going to get this equation right here, which checks out. So that's sort of the proof of that. I guess you can also just memorize that equation, but we're going to move on from that to the next step. Just give me 1 second. Okay, so we're going to show Kuratowski's theorem, and this basically says that if a graph contains k5 or k33, then the graph is non-planar. Let's see. This also checks for graphs. That also checks to see if graphs are planar or not, this equation right here. But we're going to use this example right here to show that any non-planar graphs contain one of these two graphs, a k5 or a k33. And what a k5 is it's this graph right here, and then a k33 is this bipartite graph right here. Okay, so yeah, we're going to take this and I'm going to draw it really quick. So again, in order to show that this graph is non-planar, all we have to do is show that it contains either k5 or k3,3. In this case, we're going to show that this graph contains k3,3, and we're going to do that by removing these edges and vertices right here. Just look at a subgraph of this graph. And if we remember, let me see, 1, 2, 3. I think we can also take that out too. Give me 1 second. There's also something, I forget what the term is, but where we kind of like collapse edges onto themselves. But let me see exactly what the proper coloring for this is. Okay, yes. So this is going to make sense once we actually color it. So the graph that we are going to show is the bipartite graph, the k33. So if you remember what bipartite means, it means that we can take the nodes and color them such that there's two distinct groups, and any edges that connect two vertices must be across those group lines. So, you know, let's say we have this coloring right here. As we can see, this edge is between a blue and a red, this edge is between a blue and a red, same for here. This bounces across a node, but you know, if we were to remove this node and have that direct edge, it's still between two different sets, right? And it's a similar case up here, and yeah, here too. So because we have shown that K33 is in our overarching, or it's in this graph, which is a subgraph of, to be clear, this is a subgraph of our original graph, and because K33 was in that subgraph of the original graph, then our original graph must be non-planar. And that's Kuratowski's theorem. And we're going to move on to the next section, I believe. Okay, so this one is on duality. So essentially, if two graphs are dual to each other, that means the number of vertices in one graph is equal to the number of faces in another graph. And this is how I think of it. Okay, so yeah, planar graph is the dual of a map. So two colors for each station. Yeah, so basically the country in the map becomes a node in the graph, and then an edge in the graph becomes like a border in the map. Bipartite graphs, so yeah, we sort of talked about this. It's too colorable unless there is an odd cycle, it seems like. If two vertices are the same color, are connected, and that must mean that there is an odd cycle. So we're going to say that that connection is UV. Yeah, this is sort of like, I could illustrate this, illustrate cube example. Yeah, maybe I will actually, just for good measure. So give me a second. Okay, so essentially the way that we prove this is by, the way I'm going to prove it is by taking this planar graph and making it very obviously, I guess this technically looks non-planar, but it was saying if there is an odd cycle, then it is not too colorable. So let me just make that line a bit better. And the way that we prove this is by starting at some arbitrary K vertex. Say vertex K is this one right here, and what we're going to do is travel across, and let's say this is U, vertex U, and this is U vertex V. We're going to travel across U through V, and then we're going to travel across V through U, and we're going to see that those cycles are even, but plus, this path right here, that's odd. Honestly, I don't even really know why this makes sense. I'm just following the procedure. You know what? I'm going to skip it. There are more important things to be covered. Okay, so the next part is theorem 5.4, which says that every planar graph can be colored with 5 colors. So the famous example is that it can be colored with 4 colors, but we're going to prove something weaker, as the notes say. So, as we sort of said earlier, maps of these countries can be represented as simple and planar graphs, and we're going to use the fact that at least one vertex must have degree 5 or less. That's something that they very quickly go over in the notes. I'm not entirely sure how it works, but I know using the equation, the number of edges is less than or equal to 3 times the vertex. Like, using this equation will help you arrive at that solution. Basically says that, like, if you were to have all vertices have degree 6, then the number of edges would be equal to 3 times the number of vertices, which is greater than this. So let's see. So yeah, we're going to proceed by induction. So just assume that there is, it's kind of trivial, but assume that there is a country with just, or a map with just one country. Graphically, that would look like a single node, and it's pretty obvious that we can color that node, any of the 5 colors, and that it'll work. And our induction hypothesis is going to assume that this holds for nodes greater than or equal to 1. And then we're going to have to prove that, adding n plus 1, that step in fact holds. So let's say we have a node of degree 4. And I'm going to switch over to Paint for this. So let's say we have a node of degree 4, and this would be a country. So this means that it borders 4 other countries. So, we can very easily color all of the adjacent countries different colors. And because we are given the ability to color with 5 colors, we can just color our center country a 5th color. But, given that we're using the statement that there is at least one vertex that has 5 adjacent vertices, we must actually act upon the assumption that there is another country that borders this country. So let's say it's like that. So, we can make the other countries different colors, but we can't exactly make our inside country another color so easily. So I'll just do yellow, or no, that's not yellow. So then how are we going to overcome this? They have a representation in the notes, but it's, to me, was not very intuitive at all. But essentially, the 2 cases that you can have are the following. So let's say you have a chain of, bordering countries. So we don't really know what they're going to be, but we can say, hey, maybe this borders a blue country, and then maybe this borders a red country. And maybe it's in fact possible that they connect with one another, like this. Okay. We're actually going to look at the case where they don't connect. So let's just say it's like this. So if this is the case, then in order to get a color for our middle country, we can simply color flip on this entire chain right here, because we know that will be okay, because as long as those that are next to each other are different, then we're fine. So we can make this, we can actually make this blue. So this is blue, and then, sorry, this is meant to also be blue. And then this would chain off to a red, which would then chain off to a blue because we just color flipped. And notice how this is fine, because this chain, it doesn't connect to that one, and everything adjacent to this node right here, it's all different colors. This is separated from that, right? Now, that was sort of the simpler case. What if it was the case that, and I'm gonna make this blue. What if it's the case that these actually connect, right? That was the other case. So we're gonna have a red here. So basically, if these connect, then what we can show is that a chain from, say, yellow to green would not be able to connect because the edges would cross. And in a simple planar graph, edges cannot cross. Because of that, we're going to have a situation from earlier where we have this chain that kind of goes out, and because it doesn't connect to anything local to here, we can simply color flip and then make our inside color the appropriate color. So hopefully that makes sense, and I think we're now done with this section. Okay, so we are now going to jump into the next section, which is important classes of graphs. And there's 3 that they mentioned in the notes, and I'm going to go through pretty much like what makes up each of these 3 classes. I'm not really going to go through their proofs necessarily. The last one for hypercubes, for example, is pretty confusing to just read. Hopefully the lecture tomorrow will cover it a little bit better. Okay, so what is a complete graph? It's represented by this right here, and basically it is a graph in which n nodes are connected to every other node. So an example of that would be this right here. This is K5, for example. Notice how there's 5 vertices, and each node connects to every other node. Okay? Yeah, so if the graph is directed, then that means we're going to have edges that go both ways. Right? Okay. Next, we're going to talk about a tree. I'm sure we are all pretty familiar with a tree at this point. I'm just very quickly going to go over some of the terms again. But a tree has a root. It also has leaves, which are nodes that do not have children. And then, at least in the notes, they called everything in between internal nodes. Then we have 2 things called the depth and the level. And the depth of a tree, let me switch over to Paint. The depth of a tree, and I just drew one out really quick, refers to the distance from the root to the lowest leaf. So say if we had a leaf here, the depth would technically be that. And so in this case, the depth is 1, 2, 3. And a level is simply all the nodes on a particular step, I guess, from the root. So this is level 0 right here. This is level 1. This is level 2. And level 0 encompasses all of these nodes. Level 1 encompasses all of these. 2, all of these. 3, all of these. So hopefully that makes sense. And then there are, as they've mentioned a couple times, several definitions for what a tree is, but 4 important properties for trees to keep in mind are the following. Let me switch back over to the notes window. Okay, so they must be connected and acyclic. That's just a condition of it being a tree. It has to have the number of vertices minus 1 edges. So again, a tree is the minimal number of connections needed to connect all of these vertices. And a removal of any edge disconnects G. And similarly, if you had to add an edge to G, that means you would have to go between 2 existing nodes in the tree, which would create a cycle. So these conditions all sort of overlap and kind of like imply each other. And that's what this theorem is actually going to talk about. So the statement G is connected and contains no cycles, and G is connected and has n-1 edges are equivalent. And if things are equivalent, we're going to have to say that one implies the other and the other implies the one. So if G is connected and contains no cycles, then what is it? Evolve. Then it has n-1 edges. So what did we talk about? Okay, so if we induct on vertices, one vertex has no edges, which has no cycles, and therefore the number of edges is n-1. One vertex minus 1 is 0, has 0 edges. We're going to use strong induction, assuming that everything before k value is true, and then we're going to take a step. So for k plus 1 vertices, we're going to remove an edge, and for some reason we assume the graph is still connected. If it's the case that it's connected, then we're going to roll with that and then just assume that the hypothesis holds for the subgraph. And we know that the subgraph has k minus 1 vertices, and essentially to not create any cycles, we have to add back our edge to that vertex that we removed it from. I don't know, it's not like, this sounds like super obvious to me, like I don't know why you would really need to go through all of these steps. I guess I'll just walk through this. Assume that a graph with n-1 edges must contain a cycle. So if there is a cycle, then we're going to remove an edge. So we're going to prove the converse direction, right? Which says that if G is connected and has n-1 edges, then G is connected and contains no cycles. But we're going to contradict this by saying that if it has n-1 edges, then it has a cycle. And we're going to remove an edge, because if there's a cycle and we remove an edge from it, it still should be connected, right? Because if there's a cycle, that means that there were multiple things connecting to one vertex. However, we asserted that there are n-1 edges, where n is the number of vertices. And something that we have to take for granted is that the minimum number of vertices, or of edges, that any graph can have, any connected graph can have, is the number of vertices minus 1. And I think you can prove that on your own later in the exercises, but that's something that we just have to accept. And so that poses a contradiction. Okay, the next and last category of classes, or of trees, or of graphs, graphs, is the hypercube. And, something they talked about between trees and complete graphs. So a complete graph has a bunch of connections, like the maximum number of connections to all other nodes in the graph, right? So say you have houses and they're connected to the electrical grid, and there's like power lines running between like all sources of things that use electricity. If there's a power outage that caused like one of the lines to go out, there's still like I guess n-2 lines that connect to that one node, so it still receives power. However, as we add more and more nodes in this graph, we're going to have to add exponentially more edges to ensure that each node is connected to every other node in the graph, like exactly once. However, a tree connects every vertex in the graph with the minimal number of edges possible. As we saw in our illustration, we have 1, 2, 3, 4, 5, 6, 7 edges, and we have only we have 7 vertices and 6 edges. And this isn't connected to here and like every other node, right? Because it can reach this node by traveling, through this node. However, if we think about what would happen in a power outage, as soon as this node, this edge right here, were to get cut, then power would be lost to all of these nodes right here. And this is sort of where hypercubes come into play, because they're a nice compromise between efficiency in terms of having all these connections, and in terms of having the minimal number of connections, or I guess connectivity and efficiency is how I said it. So how it works, these are some examples of hypercubes. So this is a one-dimensional hypercube, this is a two-dimensional hypercube. Oh, sorry, let me switch back over to LeetCode. So these are examples of hypercubes. This is a one-dimensional, this is a two-dimensional, and this is a three-dimensional. Basically, each vertex is represented by an n-dimensional string of bits. So since this is one-dimensional, we're going to have 2 vertices that are going to be represented by all of the bits that you can use, given that you have 1 bit, right? So you can have a 0 or you can have a 1. Similarly, this is two-dimensional, so you can have 2 bits to represent each vertex. So you can have a 0, 0, 0, 1, 1, 0, and a 1, 1. And the way that all vertices are connected is if they are exactly 1 off from one another. So I think a clear example is if we were to look at the 3-dimensional hypercube. And maybe we'll look at this 1, 0, 0, and we'll see how you can flip the second bit, and that's 1 away. If we go here, you flip that third bit, the leftmost bit, and then once you go to this one, you just flip the rightmost bit. And those are the 3 ones that it's connected to. The 3 other bits, strings of bits that are exactly 1 difference away, right? And given these facts, we're going to say that the number of edges in an n-dimensional hypercube is n times 2 to the n divided by 2. Okay, so as we can see, the number of vertices in a hypercube is dependent on the dimension of it. So, and I think I actually drew out something similar when we were talking about power sets in note 0, but let's say we have this right here, a 2-dimensional hypercube. And if I remember correctly, it was like this. And we can actually reuse this tree right here. It's better for the environment anyways. And basically, we're going to have this list that's going to represent all of our, like, each possible combination. And at each level, we're going to make a decision for each bit. So, you know, at this level, we can choose to have 0 as our first bit, but maybe on this node, we choose to have 1 as our first bit. And then once we've decided what our first bit is, then we're going to look at the second bit, and we can again decide to make that second bit a 0, or we can decide to make that second bit a 1. Similarly, we can do that. And because for each level we go down, we get 2 more choices per each previous choice. We get this 2 to the n relationship between number of vertices and, 2 to the n is the number of vertices. Okay. And so that's why we have the 2 to the n in the equation. We also have, again, we're trying to calculate the number of edges. So something we can notice is that from each vertex, we have exactly n edges coming out of that. And how is this possible? Well, let's look at this number 100, right? For every n-bit string, there are n other n-bit strings that are 1 different from it, right? Because you can only change each of these bits in 1 way. If you were to change 2 bits, then obviously it would be 2 away, and so you couldn't do that, right? So notice how everything that 1, 0, 0 is connected to is exactly, 1 away. And notice how that's also the dimension of this hypercube. So we're going to have the number of edges coming out of each vertex times the number of vertices, and then we're going to divide that by 2, because we should notice that an edge connects 2 vertices, right? So if we sum the number of edges coming out of every vertex, we're going to double count the edges, because, an edge is between those 2 vertices. So we have to divide by 2, and that will yield the number of edges in our hypercube. So this sort of explains that. And with that, I'm not going to go over that last theorem. I'm going to leave it for the professors to do that. And that about wraps up Note 5 of CS70. This has been an intro, but a pretty thorough intro to graph theory.